the model that explains everything. Except one thing. For decades, physicists believed they were getting closer to a complete understanding of reality. The standard model of particle physics emerged as one of the most successful scientific theories ever created, accurately describing the fundamental particles and 3 of the 4 forces that govern the universe. It explains how matter interacts, how energy moves, and how the microscopic world behaves with astonishing precision. Experiments have confirmed its predictions again and again, making it seem almost complete. Almost, because hidden within this elegant framework is a glaring absence, something so fundamental that its absence feels impossible to ignore. Like gravity, the force that shapes galaxies, bends light, and holds the universe together, is nowhere to be found in the standard model. While the theory works perfectly for the quantum world, it says nothing about the force we experience every day. And this creates a striking contrast, a model that explains almost everything, yet fails to include one of the most obvious aspects of reality. So the question remains, quietly unsettling everything we thought we understood. If our best theory cannot explain gravity, how complete is our understanding of the universe? Really? At first, this might seem like a minor gap, a detail waiting to be filled, but the deeper you look, the stranger it becomes. Because gravity is not just another force, it is woven into the fabric of space and time itself. Leaving it out is not a small mistake. It is a fundamental fracture in our picture of reality. And that fracture leads to an even bigger mystery, one that scientists have been trying to solve for decades. Because if gravity doesn't belong here, then where does it truly fit? And what does that say about the problem with gravity, where physics breaks down? At first, scientists assumed gravity would eventually fit into the same framework as the other forces. After all, electromagnetism and the nuclear forces had already been unified within the standard model described through quantum fields and particle interactions. It seemed reasonable to expect gravity would follow the same rules, but it doesn't. The problem begins with how we understand the universe at different scales. The standard model operates a world where particles behave like probabilities and forces are carried by discrete units. In this realm, everything is quantized, broken into the smallest possible pieces. Gravity, however, refuses to behave this way. Instead of acting through particles in a simple quantum framework, it is described by general relativity as the curvature of spacetime itself. Massive objects don't just pull on each other, they warp the very stage on which reality unfolds. This creates a deep contradiction. One theory describes a universe made of tiny, discrete interactions, while the other describes a smooth, continuous fabric. When physicists try to combine these ideas, the math collapses into infinities that cannot be resolved. Predictions lose meaning, and the equations stop describing anything physically real. What works perfectly on its own becomes unstable when forced together. This is where the illusion of understanding begins to crack. The standard model is incredibly accurate, but only within its own domain. General relativity is equally powerful, but only on cosmic scales. Between them lies a gap that no theory has successfully bridged, and the deeper scientists push into this boundary, the clearer it becomes that something is missing. Not just a piece of the puzzle, but perhaps an entirely new way of thinking about reality itself. Beyond the standard model, the search for a deeper theory, if gravity refuses to fit into the standard model, then the problem may not be gravity at all. It may be the framework itself. This realization has pushed physicists toward a bold idea that our current theories are not the final picture, but only proximus. One of the leading approaches is string theory, which suggests that the fundamental building blocks of reality are not particles, tiny vibrating strings. In this framework, gravity naturally appears as a quantum particle called the graviton, offering a possible bridge between quantum mechanics and space-time. Another direction, loop quantum gravity, attempts to quantize space-time itself, breaking it into discrete units and reshaping how we understand the fabric of the universe. Both approaches are elegant, ambitious, and still unproven. There is no experimental confirmation yet, only mathematical consistency and indirect hints. That makes the search both exciting and uncertain. What makes this pursuit so important is what lies at stake. A successful theory would not just add gravity to the standard model. It would unify all forces, explain the origins of the universe, and reveal what happens inside black holes, dot